Welcome to Ask and Learn.
Here we have nitrogen entering a diffuser. So we have nitrogen and the ideal gas constant. It's entering at 100 kilopascals on 110 degrees C at a velocity of 205 meters per second. And it leaves at a slightly higher pressure of 110 kilopascals, but a much lower velocity of 45 meters per second, which is what a diffuser is for. Let's see here. We're told that we estimate a heat loss of 2.5 kilojoules per kilogram. And the surroundings are 27 C and 100 kilopascals. And the diffuser, the exit area is 0.04 square meters. So we want to figure out the accounting for the variation of the specific heats with temperature. Okay, so need to be a little careful here. Determine A, the exit temperature, B, the rate of exergy destruction, and the second law efficiency. Okay, then. Well, since we can't use the simple analysis of just using constant heat capacity. We got to go to the tables, or the software. So we know these properties here, so we can look up or have the software spit out the enthalpy and the entropy at the inlet. And then we also have the enthalpy and the entropy of nitrogen at the surrounding conditions. And so, yeah, they wanted to know some about exergy at the inlet. So we needed that at some point or to get the second law efficiency. So what we can do then is energy balance. Okay, so this is a steady flow process. So the energy flow in, the specific energy flow in, the specific energy flow out, and then the heat transfer out. And in this equation, we know everything but H2. So that allows us to figure out what the enthalpy at the exit is. And we also know the pressure at the exit. So now we have two properties of the exit. So we can use the software or look on tables to figure out what the temperature and the entropy are at the exit. We can figure out the mass flow rate because we know what the area is and we know what the, let's see here, we know what the area is and we know what the, and I messed up, I made these should be velocity V's, maybe not in red. Velocity at 2 and velocity at 2. All right, so that's much better. So we know that, again, this is the cross-sectional area times the velocity that's flowing through there. So this would be the volume flow rate, and then we can divide through by the specific volume to get the mass flow rate. All right. We can then, use the ideal gas law to get the specific volume in terms of the pressure and the temperature. And then now we know all of this stuff. We could have calculated this, but just plugging this all in, we know all of this stuff, and we get a mass flow rate of about 1.67 kilograms per second. So we want to know the exergy destruction in the nozzle is the exergy difference between the inlet and the exit of the diffuser. So we have the exergy. Wait a minute. I did not copy that down from my notes. Okay, well, let's do that on the fly here. I just realized that I didn't answer part of the question. So let's see here. Exergy destroyed. And that is the mass flow rate times the quantity, the H1 minus H2, plus V tilted, 1 squared, minus V tilted 2 squared, all over 2. So the difference in kinetic energy, and then minus T naught times S1 minus S2, right? So that we have that. And so we actually, we know everything here. So we can just plug in numbers. And so in my notes, I wound up with a value of 12.4 kilowatts. So that's the exergy destroyed. So now let's go back to the second law efficiency. And for the second law efficiency, we want to figure out, for this diffuser anyway, we're going to say it's the rate of exergy flowing out divided by the rate of exergy flowing in. Again, this is not necessarily a great definition. In reality, we're really covering nothing here, just like we were in expansion valve. But again, if you want to compare diffusers, this is a better way of defining a second law efficiency. Or I don't know what really, in my stickler point of view, you shouldn't even call it a second law efficiency. It's an efficiency value. But anyway, so we have, we need to figure out we have the exergy destroyed already. And so we can figure out the exergy flow rate out, because if we just know what the exergy flow rate in. So with exergy flow rate in is m dot times this difference here. In the dead state, the velocity is 0. And then the kind of the entropy-like terms here, or the entropy terms here. Again, all reference to the dead state. And so we can see the exergy flow in is 51, or about 52 kilowatts. And so the exergy at the outlet is this minus what was destroyed. And putting that in, we wind up with the efficiency is 1 minus the rate of exergy destruction divided by the rate of exergy coming in. And in this case, we wind up with 76.1%. So again, it's a way of defining an efficiency of the diffuser, but we're really not recovering any of this work that we could have possibly recovered from this exergy that was destroyed. So again, you could really say that the second law efficiency, in a very rigorous point of view, would be 0, just like it was for the expansion valve.